Hello everyone, welcome to lecture 2 on systems engineering. In this lecture, we will discuss the structure of complex system. As a quick recap of our last lecture, we defined system as a series of interrelated components that they work toward a common goal. These components must be diverse from different disciplines like mechanical, electrical, computer, civil, and so on. They are interconnected and they are engineered. A job of a system engineer is to balance conflicting objectives, to balance the tension between performance, cost, and schedule to meet the requirements throughout the life cycle, to make sure the compatibility and also functionality of subsystems. Thanks for providing your examples or the systems of interest in discussion in lecture 1. Here are some examples that I picked, but there were many more interesting examples. A battery manufacturing plant, not a battery, but the factory that manufacture the battery, consider a system. A race car is a system. A factory that makes a race car is also a system. It can be a process like a carbon capture process or the water desalination, making sweet water from seawater. Many other examples like the nuclear reactor, a spacecraft, autonomous car, the Vancouver SkyTrain if you live in Vancouver, a baking manufacturer plant, and also the pulp and paper facility at the University of British Columbia. These are many examples, and you may have your own example. In this lecture, we are going to focus on some key concepts on the hierarchical of structure of a system, which we will go with this format. We'll break down a system to subsystems, components, subcomponents, and then parts. And as a system engineer, we will focus on the interface between the subsystems, between components and subcomponents, the trade-off analysis between the performance of, again, each component or subcomponent and so on, and making sure that we balance the design across these hierarchy of our system. To have a formal definition of this model, a system will say it performs a significant useful service or a function. Subsystems, they provide significant functions. And then we have the component in the middle level, building block. Subcomponent, they provide elementary functions. Like, let's say, a gearbox in a system, it provides the transformation of power from one shaft to another shaft. So it's a subcomponent. A part by itself, it doesn't have any function. A gear doesn't have a function unless we combine it with another gear in a gearbox, then it has a function. As a quick example, a simple example, an airplane. Consider an airplane as a system. One of its subsystems is the engines. And then the component of an engines, one of its components is thrust generator. A subcomponent of thrust generator is the turbine, and a part of this subcomponent or the turbine is a blade. Let's look at another example, an antenna position control system. Let's assume it is a subsystem of a larger communication system, this antenna. This larger communication system can be a satellite, a radar, a telecommunication networks, a radio systems, or a broadcast systems. I want you to pause the video and try to see if you can identify the components, subcomponents, and parts in antenna position control system. Right? So in other words, our goal here, we consider antenna, the azimuth antenna position control system, which I'll show a schematic here for you on this slide. Assume this is our subsystem. How would you go to break it down to its components, subcomponents, and parts? All right. Again, you can pause the video and think about it. Well, this is how I break it down. You may do it differently. Well, I said my subsystem is the antenna. It is part of a communication system. It works with many other subsystems in the communication system. I break it down to two main components, the forward motor driving systems. So look at the schematic. From the potentiometer, you provide a rotation. The potentiometer converts your rotational, mechanical rotation to a signal. It sends the signal to an amplifier, and then the amplifier sends the voltage to a motor, perhaps a DC servo motor. Then the motor rotates a gear. That gear interacts with a larger gear, and as a result, they rotate the antenna. We need to also have a feedback, making sure that when I give an input to potentiometer, if the antenna is the position that I want. So we add an equal or maybe the same gear attached to working with the gear that connected to our antenna, and we attach a potentiometer to that gear as you see on the picture there. So as a result, the potentiometer again is going to convert the rotation of this last gear to electricity, returning back to the amplifier. Now our amplifier is going to compare our input signal to the feedback signal, right, from the antenna, and then provide the signal to the motor and so on. You do not need, if it is not your electrical or electromechanical system, is not your subject, you do not need to details of that. But at least you should understand the functionality of each component. Gears, what is its function? A DC motor, what is its function? An antenna to receive or perhaps sending signals. A potentiometer, which converts the mechanical rotation to electricity. As long as you have a general idea, you should be able to break it down to its components and so on. So let's go back. Our components are the motor drive systems, and the other component can be the feedback control system from the potentiometer going back to the amplifier. The subcomponents now, let's say for the motor drive systems, can be the DC servo motor. For the feedback control system, we have other subcomponent, but you can think about, for example, the encoder's potentiometer and so on. Parts, remember, they do not do a function alone. For example, bearings, gears, connectors, wires, and so on, they are part. Please work on this system and see how you may perhaps break it down to its components and parts. Well, we also talk in lecture 1 about complexity of modern systems, that the key challenges are the number of components are perhaps too many, and we sometimes integrate a system like this antenna to a bigger system, and that bigger system perhaps is part of another system. That's why the term SOS or systems of systems sometimes discussed, which we will also discuss in this course as well. So the best approach then to deal with this complexity is the model-based system engineering. With that, we can manage the interfaces, we can detect inconsistency in our system, and we ensure effective communication across subsystems and the team that works across subsystems. But how do we do that? Well, I'm just going to provide a few terminologies before we talk about the model-based system engineering. Operand. Operand essentially is the input or the material that the system works with, or the system manipulates, transform, interact with it. To provide a better explanation, let's look at the characteristics of operands. Operand can be physical or abstract. Physical, like the material, energy, components, like a sheet metal that we build the body of a car or the fuselage of an airplane. Or it can be abstract, like the data, the signals, or the information. Operands interact with system through functions, right? If the function of a system is, let's say, to convert or form, let's say, a sheet, a metal sheet for to make a body of a car, then that process or function works with an operand, and the operand here is the sheet metal. Well, what is the role of operand in a system functions? Without operand, without material, without input, there is no function. And it's talking about functions is going to be meaningless. Examples of operands in a manufacturing setup, the raw material, the sheet metal that I talk about. In a communication system, the data and signals. In a transportation system, think about passengers and goods and other things that we want to transport from one point to another. In an energy system, fuel or power or electricity and so on, they are all operands. Well, it's important in system engineering to understand actually the role of operands, because first of all, it helps us to define better the requirement of the system. Am I working with electricity? Am I working with fuel? Is this process involve working with sheet metal? What type of metals? And also, when I'm designing the functional elements, if I know what sort of material I'm going to deal with, I'm going to work with data, or I'm going to work with, let's say, a chemical, then I can design my functional elements perhaps in a meaningful way. And also, I know the interface design, how, let's say, the antenna example, the electromechanical system is going to interact with, let's say, the DC motor with the gears, and so on. Form. In a system, in the context of a system, form refers to structure of the system. Some key aspect of form, a physical structure, like the tangible geometry, like a chassis of a car. The configuration, the way that we put the parts or components to work together. The material composition in constructing our system, and the interconnection and organization of the system, they gives us the form of the system. Now we can talk about these system building blocks. We can divide the building block of systems to two main attributes, the functional elements and the physical components. The functional elements can be divided to four categories: the signal, data, material, and energy. Criteria to be a functional element: it must be significant, so it must perform a significant function. It must be singular. What do I mean? Let's say fall with one of technical scope. For example, a gearbox fall with the mechanical scope of our system. A DC motor fall with the electromechanical aspect of our scope of our system. And also common, we should see the function perform in other systems, like a gearbox can be in an antenna, can be in a car, in an airplane, in a helicopter. So it's common function that can be found in many other variety of system, unless we invented a new system which has a particular function for that system. That's a different story. And physical components, it can be electronic, mechanical, thermomechanical, or software. For example, a signal processor in an electronic system, a framework or a chassis is a mechanical system, a heating unit, and operating systems. So now we can talk about the knowledge domain of system engineers versus design specialists. Remember in lecture 1, we talked about the breadth of knowledge that the system engineer must have, And if you recall, we said a system engineer must be specialized in at least one domain, mechanical or electrical or software in one. And then he must know a little bit of other domains. But how much? Well, let me show you a diagram. As we said, we can break down a system to subcomponents, subsystems, components, subcomponents, and parts. Now, we can say that a design specialist must be specialized in designing parts, must also know a little bit about subcomponents, and its knowledge extend up to the components. But on the other hand, a system engineer, he knows how the system works. What are the four, let's say, main category subsystems, how they interact with signal, data, and materials. And these two, they overlap at the component level. And this is where the communication is important. This is where the system engineer asks our engineer, the specialist, about the component. And perhaps he needs a little bit more information about how the subcomponent work, but he does not need to know the detailed design of, let's say, a helical gear or a detailed design of magnetic field in electromechanical DC servo motor system. So again, a system engineer then works from the extend his knowledge from the system level down to the component, and at the component level, the system engineer communicates with the design specialist and asks more details. Environment. Another terminology that we will talk about the context of system engineer a lot is environment. Anything outside the system that interact with our system is called environment. It can be the operator, like the human in a car. It can be the repair or the maintenance guy who fix our car. That also consider an environment. It can be the support system like the road, the power grid, or threats, the weather, or maybe the theft. They also interact with our system. Speaking of a car, we can, rather than documenting all this information, let's say we can create a context diagram for a car. But what is a context diagram? Simply, we will show the system as a black box right in the middle, like this ellipse shape that I call it the system. And then we will show the external entities that interact with our system as these boxes around it. And that arrows represent the flow of information or material, either abstract or physical operands. Let's go to the concept of a car. So for a car, the user provides commands to the car, the maintenance exchange part, and also after he finds out the diagnostic information relating to the car. The energy source is the fuel, and the environment is again the road and the weather and so on. If I show it in a context diagram, you see the car is in the middle. The user's maintainer, like the repair guy, and the environment and energy source, those are the external entities. And the arrows shows the interactions. If the arrows is toward the system, it means what, let's say, the user gives to the system, like it gives the command of steering, the braking, the acceleration, the light, and so on. In return, the automobile returns back the transportation, it gives entertainment, and it gives return back many other, let's say, information or service or functions to the users. The same is about the environment. What environment gives to our system and what the system gets in return. And so on. You can work on this context diagram in more details. Few words about interfaces and interactions. As we said, the interfaces between the subsystems or components. It can be connectors, isolators, and converters. In the context of the antenna example, which makes a little bit more sense, the connectors can be cables. They connect, let's say, the potentiometer to the amplifier and the amplifier to the motor and so on. So cables facilitate transmission. It can be the gears. The gears also transmit power from one shaft to another shaft. Isolators inhibit the interactions. For example, the bearings isolate the interaction of gear with, let's say, the gearbox shell or with the other components in the system. So it put in place the gears. The converters change the form. For example, the potentiometer convert the mechanical rotation to signal or to electricity. You can see more examples in this table. The type of connectors or isolator in an electrical system, for example, a switch is a connectors. In a mechanical system, a joint coupling, and so on. You can again pause the video and check this table with more details. Moving on, some general principles of interface design. These are very generic. When we design interface, we should keep the interface simple and maintain isolation. It means avoiding unnecessary interaction between subsystems. So we will do the interactions when it's necessary. Obviously, in the example of antenna, our DC motor has to interact with the gears, but there is no necessity for the motor to interact with the antenna directly. And the Murphy's law. Most likely you've heard the Murphy's laws. When something can go wrong, it goes wrong, right? I just found this example of Apollo 13 oxygen tank failure. I'm going to put the link below, and which you can listen more to the story and the technical details, what goes wrong. Based on what I've heard and I read, again, there are more details. There is this little switch, a thermostat switch, which at some point NASA decided to go from 28 volt to 60 or something volts, but the subcontractor fails to tell to one of its supplier to change the switch to these 60 something volts. And apparently that switch failed. However, there are many more details which I not gonna provide you wrong information. Please go through that. That's a lot of things that you can learn from the example of Apollo 13 oxygen tank failure. A little bit on principle of subsystem design. When we design subsystems, we should follow these principles, and I adapted from the art and science of systems engineering and from NASA. Principle number one, apply equal sweat. So distribute the function between subsystems equally. Maintain healthy tension between subsystems. You don't want to increase the performance of one subsystems, but decrease the efficiency of another subsystem. Manage margin. It means have a tighter requirements. And in that case, you create capability. If, let's say, your requirement is go up to 100 something, then why not you set your requirement to 120? Then in that case, if you succeed, it means you created a capability. Produce a robust design, and then identify the gaps and overlaps and more like detailed design, and then study unintended consequences. A little bit more details. Equal sweat. So as I said, distribute the performance and functional equally as much as possible between subsystems. So you do not design your system in a way that one subsystem does majority of the work. Of course, effective communication between team members, reallocation, and many other details, which you can, again, pause the video and think about it and perhaps look at different examples. Healthy tension. Uh, as we said it again and again, job of system engineer is to balance actually the objective between different subsystems and different teams and manage the cost, schedule, and technical goals. You can look again at different examples as well for that. A robust design, a design that can tolerate, let's say, a change um, or a fault tolerance. Uh, let's say if one component fail, can the system still function? Go over gaps and overlaps, review the requirement, analyze interface, and also detect gaps early in the design without to prevent then a big delay later in the process. As I said, if you set your requirement a little bit tougher, then it means, or you set up some contingency, then you are creating a capability. Let's say the requirement is this middle cloud there. You set your requirement a little bit tougher. So that's the margin. So you are creating a capability. The key takeaways, the interface design, keep them simple, isolate them, and also adaptability between interface between subsystems. The equal sweat, fair allocation of requirement across subsystems, healthy tension, and balancing the cost, schedule, and technical goals, and have a robust design. So failure of one component should not result in failing of the entire system. Here I'm just going to go over a case study for aircraft. So sort of we're going to go through what we discussed as an example for an aircraft. First of all, we review the aircraft in lecture 1 and this cartoon that shows the tension between different, let's say, groups or subsystems between the fuselage, the body of the airplane, the weight, and each team, and they believe they are the most important, the aerodynamics groups, they want their design, something that performs the best aerodynamics. But the fuselage group, they want to have the maximum capacity inside the fuselage. And the weight group, of course, they want to build the airplane out of wood, perhaps, and make it as thin as possible, and so on. So aircraft requires system engineering approach because it's a complex system. There is many components and there is interactions between them. It requires system thinking, like a holistic integration of all components and alignment with customers and their regulations as well. So if I break down the aircraft to its subsystems, I can break it down to airframe, propulsion, avionics, landing gears, and electrical systems. And the key processes in aircraft system engineering: requirement analysis. What is the user needs? What are the regulations? What are we designing the airplane for? The functional allocation, like we need to allocate a specific function to subsystems. Again, going back to the subsystem, what is the function of avionic, the navigation of the system? What is the function of the airframe, and so on? System synthesis, develop and integrate physical subsystems. And then we'll move to V&V, verification and validation, which means we test the subsystems and the complete system. Again, for example, a flight control system, the functional requirement is the stability and control, the allocation, avionics, and hydraulics. An example of subsystem integration, the avionics and the flight control. Avionic integration inputs for navigation of an airplane or the sensors, the data, like the altitude, the speed, and so on. The output is the commands to control the, uh, the airplane, some components. And the challenge is the interface management between hardware and software. Verification and validation. Perhaps you may do wind tunnel testing, or you may do flight simulation to validate and verify your subsystems and the system, the entire system as well. Again, system thinking as a holistic mindset in aircraft design, the key principle is to understand the aircraft as an interconnected system. Analyze the trade-off to balance the performance, safety, the cost, and the technical goals. And of course, go through rigorous iterative development to refine the design through multiple cycles. An example of trade-off, increasing the fuel efficiency versus adding weight to make the structure more stronger and safer. Some common challenges in aircraft system engineering, the interface management. So making sure there is a great communication or a thorough, meticulous communication between subsystems. Safety and reliability, designing for a robust design to avoid, let's say, fault. And if there is a fault in one component, the system can tolerate it as a whole. Regulatory compliance, meeting goal, aviation standard. Depends on which country or which airport we are designing it for. And the cost management, balancing development costs with the market demands. So some highlights. Aircraft is a complex system, integration of many subsystems, which required a structural approach. Key processes, requirement analysis, functional allocation, synthesis, validation, and verification. Holistic thinking ensures safety, performance, and compliance with the regulation. To summarize our today's discussion, the key takeaways, system hierarchy can be modeled as subsystems, components, subcomponents, and parts. These entities, they interact with each other. These interaction, which we'll call them interfaces, can be the connection, isolation, and convert interactions, converting one form of entity to another. The environment, defining the boundaries and the interaction. Environment is anything that interact with our system. A human is considered an environment for a car. Weather consider or road considers environment for a car. And complexity, utilize model-based system engineering for effective management. Thanks for listening. Here are some questions and discussions to reflect on, and perhaps in discussion 2 below you can provide the hierarchy of system of your interest. Perhaps the systems that in lecture 1 you provided that piqued your interest, and try to break it down to its subcomponents, components, and parts. Thank you very much.